Alright, let's go. Number 10. The Second Law of Thermodynamics. In 1850, Rudolf Clausius was not trying to unsettle anyone. He was trying to fix steam engines. Working in Berlin, he wanted to understand why real engines always lost usable energy as heat, no matter how well built they were. He was solving an industrial problem, not a philosophical one. Newton's laws and every fundamental equation of motion since work identically whether you run time forward or backward. A billiard ball's collision looks equally valid played in reverse. Nothing in the underlying mathematics prefers one direction of time over the other. That was the accepted picture. Then Clausius formalized a quantity he called entropy, and found it never decreased in an isolated system. Ever, not once, not by accident, not under any known condition. Clausius published his formulation of the second law in 1865, coining the term entropy from the Greek for transformation. Later, Ludwig Boltzmann at the University of Vienna gave it a statistical backbone. Showing entropy measures the number of ways a system's particles can be arranged. The universe, it turned out, is dragged relentlessly toward its most probable, most disordered configurations. Physicists tried to explain away the asymmetry. Some argued it was just a local statistical fluke, valid only in our corner of the cosmos. Others proposed hidden variables that would restore time symmetry at a deeper level. Neither survived scrutiny. Every experiment, every engine, every dissolving sugar cube confirmed the same one-way street, and no one could explain why the fundamental laws underneath allowed it. If entropy always increases, then the wrinkles on your hands, the fading of a photograph. The last breath you will ever take are not separate events. They are the same law of physics, expressing itself once. You are not aging. You are entropy, wearing a name. Why does a universe built from perfectly reversible laws produce a life that can only ever move forward? Loschmidt shrugged and asked the question that has never stopped echoing. Number 9. Loschmidt's Paradox. In 1876, Johann Joseph Loschmidt was a friend and colleague of Boltzmann in Vienna, and he was trying to help, not to demolish anything. He was checking Boltzmann's new kinetic theory of gases, the same theory that had just explained entropy statistically. He assumed he was confirming it. Boltzmann's H-theorem predicted that a gas would evolve from any starting arrangement toward equilibrium, and stay there, an apparently one-directional process baked into the mathematics of colliding molecules. That was the setup Loschmidt was working from. Loschmidt realized that if you took any gas evolving correctly toward equilibrium and mathematically reversed every particle's velocity, the reverse system was equally valid under Newton's laws, and it would evolve backward, away from equilibrium, unmixing itself. Loschmidt presented this reversibility objection directly to Boltzmann in Vienna in 1876, pointing out that a time-symmetric underlying dynamics cannot, by pure logic, produce a result that is only ever true in one time direction. Boltzmann never fully answered it. He eventually retreated to probability, arguing reversal was allowed, but staggeringly unlikely. Scientists proposed that true reversal was simply too improbable to matter. But improbable is not impossible, and the objection stood on pure logic, not likelihood. Others suggested Boltzmann's assumption of molecular chaos secretly smuggled in the arrow of time. That critique still has defenders today. No one has closed the loop. Somewhere, in principle, there exists a version of every shattered glass on your kitchen floor reassembling itself. The laws do not forbid it. They only make it absurdly, almost insultingly unlikely. If the laws don't require the past to be different from the future, why does reality only ever seem to write the story forward? That absurd improbability had to come from somewhere, and the beginning of everything is where it starts. Number 8. The Low-Entropy Big Bang Problem. Roger Penrose at Oxford was not trying to explain the origin of time's arrow when he began analyzing gravitational entropy in the 1970s. He was working on singularity theorems, the mathematics of collapsing stars alongside Stephen Hawking. If entropy always increases, then the further back you trace the universe, the lower its entropy should have been. Standard cosmology agreed. But nothing in the equations said the initial state had to be low entropy at all. Any starting configuration was mathematically permitted. Penrose calculated exactly how special that starting state needed to be, and the number was not just low. It was absurd. Penrose estimated the probability of the universe's initial low-entropy configuration occurring by chance at roughly 1 in 10 to the power of 10 to the power of 123, a figure he published across several papers and his 1989 book discussions of gravitational entropy. No comparable number exists anywhere else in physics. Inflationary cosmology was proposed as a fix, smoothing the early universe into its observed state. But Penrose himself objected that inflation requires its own special initial conditions to even begin, simply relocating the fine-tuning rather than solving it. Other physicists proposed anthropic reasoning, that we only observe a low-entropy start because life requires one. Critics call that an explanation that explains nothing. Every structure you have ever loved, every star, every cell in your body, was only possible because the universe began in a state so improbable it borders on the impossible. You are a debt being paid off, entropy unit by entropy unit. What or who set the dial that precisely? And why does the universe owe anything at all? That debt has a due date, and physicists have already calculated it. Number 7. Heat death as the universe's endpoint. In the 1850s, William Thomson, later Lord Kelvin, was studying energy conservation in Clausius's new thermodynamics, trying to understand engines and the transfer of heat, an entirely practical Victorian concern about efficiency. If entropy only increases, and the universe is a closed system, the second law does not stop at your kitchen or your engine room. It applies to everything, forever, without exception, until there is nothing left to transform. Kelvin followed the logic to its conclusion, and it terminated in silence. Every star burning out, every gradient flattening, no motion, no work, no change. Kelvin described this eventual state in his 1852 paper on the dissipation of mechanical energy, and modern cosmologists like Fred Adams and Gregory Laughlin, in their 1997 paper in Reviews of Modern Physics, extended the timeline out past 10 to the power of 100 years, describing a universe of cold, diffuse, maximally disordered radiation. Some physicists proposed a cyclic universe that resets before heat death arrives. Others suggested vacuum decay or quantum fluctuations could spontaneously birth new low-entropy pockets, a so-called Boltzmann brane scenario, which then raises its own unsettling implications about whether observers like you are even typical. Neither idea has observational support. Every conversation you have ever had, every civilization that will ever exist, is a brief, localized rebellion against a fate the mathematics considers essentially certain. Not tragic, just thermodynamic. If disorder always wins eventually, was organized, structured existence ever the rule, or only ever a temporary, cosmic accident? Boltzmann had already found a loophole in that certainty, and it terrified even him. Number 6. Boltzmann's statistical argument. Ludwig Boltzmann, defending his own kinetic theory against Loschmidt's objection in Vienna in the late 1870s, was not trying to weaken the second law. He was trying to rescue it from a fatal logical contradiction. The second law had been treated as an absolute mechanical certainty, something as inviolable as conservation of energy. That was the assumption everyone, including Boltzmann himself, had been operating under. Boltzmann conceded something remarkable under pressure. Entropy increase is not physically forced at all. It is only statistical. Reversals are allowed. They are just extraordinarily unlikely. Boltzmann formalized this in his 1877 paper for the Vienna Academy of Sciences, showing entropy corresponds to the logarithm of the number of microscopic arrangements matching a macroscopic state, meaning the second law is now understood as probabilistic, not absolute. However, astronomically the odds are stacked. Some physicists tried to argue the improbable reversals were effectively impossible, and therefore irrelevant to real physics. But statistically irrelevant is not the same as forbidden, and Boltzmann's own mathematics guaranteed that, given enough time, fluctuations toward lower entropy must eventually occur somewhere. No proof has ever closed that door. Somewhere in an unfathomably distant future, or in some unreachable pocket of an infinite universe, your exact atoms could spontaneously reassemble from scattered dust. Statistically permitted. Practically, you will never know if it already happened to a version of you. If the law that shapes your entire life is only ever a matter of overwhelming odds. Is time's arrow a law of nature, or just the biggest coincidence ever measured? Even particles themselves, it turns out, don't fully agree that time only moves one way. Number 5. CP violations tiny time asymmetry. In 1964, James Cronin and Val Fitch, working at Brookhaven National Laboratory, were not hunting for a broken symmetry of time. They were testing neutral kaon particles to confirm that combined charge parity symmetry held perfectly, as everyone expected it should. Physicists believed CP symmetry was exact, meaning a particle and its mirrored antiparticle should behave identically. Under the CP theorem, that also meant T-symmetry, time reversal, should hold cleanly at the quantum level too. Cronin and Fitch found neutral kaons decaying in a way that broke CP symmetry outright, a tiny but unmistakable asymmetry between matter and antimatter behavior. Cronin and Fitch published their result in Physical Review Letters in 1964, and decades later the Baybar collaboration at SLAC, led by researchers including J.P. Lees, published direct evidence of T-violation itself in Physical Review Letters in November 2012, using entangled B mesons to show time-reverse processes occur at measurably different rates. Physicists proposed the asymmetry might be an experimental artifact. It wasn't. It has been reproduced repeatedly. Others hoped CPT symmetry itself might eventually break, restoring some deeper balance. It hasn't broken in any experiment run since. The asymmetry simply exists, unexplained at a foundational level, and is one of the leading suspects for why the universe contains more matter than antimatter at all. You exist, instead of being annihilated in a perfectly balanced soup of matter and antimatter, because of this exact, measured, minuscule preference physics has for one direction of time over its reverse. If even particles quietly prefer one arrow of time, why does the deeper mathematics keep insisting they shouldn't care at all? Your own memory follows that same one-way arrow, and some physicists think that's not a coincidence. Number 4. The psychological arrow versus the physical arrow. Arthur Eddington, at Cambridge in the 1920s, was not originally trying to explain human memory. He coined the phrase the arrow of time while attempting to reconcile relativity and thermodynamics into a single coherent picture of physical reality. Human experience insists the past is fixed and knowable, while the future is open and uncertain. Memory only ever runs backward in time, never forward. This feels like an obvious separate fact about consciousness. Eddington argued this psychological arrow is not separate from physics at all. It is entropy, again wearing a different mask. Physicist David Albert, in his 2000 book Time and Chance, and cosmologist Sean Carroll, in his 2010 book From Eternity to Here, both formalized the argument that memory formation requires local entropy to increase as records are laid down, meaning you can only remember directions in time where disorder has already grown. Some philosophers proposed consciousness might have an independent, non-thermodynamic sense of time's flow. No physical mechanism for that has ever been found. Others argued memory is simply correlation, not true temporal experience, which only pushes the mystery into philosophy of mind rather than resolving it in physics. Every memory you have ever formed exists only because entropy increased while you were forming it. Your childhood is not stored. It is thermodynamic residue, and it only points one way because disorder does too. If your memory is just entropy's fingerprint, is anything about your sense of a personal past actually separate from a boiling kettle losing heat? Even that fingerprint may not survive intact near the strangest objects in the universe. Number 3. Black holes and information retention. Stephen Hawking, at Cambridge in the mid-1970s, was not trying to threaten quantum mechanics. He was calculating what happens to particles near a black hole's event horizon, applying quantum field theory to Einstein's general relativity, a purely technical exercise in mathematical physics. Quantum mechanics guarantees information can never be truly destroyed. A system's future state must always, in principle, allow you to reconstruct its past. This unitarity is one of quantum theory's most sacred rules. Hawking found that black holes radiate particles and slowly evaporate, and the radiation appeared to carry no information about whatever fell in. When the black hole vanished completely, the information seemed to vanish with it. Hawking published his findings in a 1976 paper in Physical Review D titled Breakdown of Predictability in Gravitational Collapse, directly stating that gravitational collapse could violate quantum determinism, a claim he spent the following decades trying, and largely failing to walk back. Physicists proposed information escapes hidden in subtle correlations within the radiation. Others proposed a firewall of high-energy particles at the horizon, destroying anything crossing it, which conflicts with general relativity's own predictions. Hawking himself conceded a bet on the subject in 2004, but no complete, agreed-upon mechanism for how the information actually gets out has been established even now. If information cannot be destroyed, then anything that ever fell into a black hole, including hypothetically you, is never truly gone. It is smeared into a correlation nobody currently knows how to read. Does time reversal even mean anything at the one place in the universe where cause and effect apparently break down completely? At the deepest level of all, the equations themselves refuse to pick a direction. Number 2. Quantum mechanics times symmetry. Erwin Schrödinger in Zurich in 1926 was not trying to settle questions about time's direction. He was trying to describe how a quantum system's wave function evolves, building the central equation that would define quantum mechanics. Classical mechanics already had time-symmetric equations of motion. Physicists assumed quantum mechanics, as a deeper theory, would eventually reveal some hidden asymmetry that classical physics had missed. It didn't. The Schrödinger equation runs forward and backward in time with identical mathematical validity, just like Newton's laws before it. Physicist Eugene Wigner formalized time reversal symmetry within quantum theory in his 1932 paper, showing the underlying dynamics obey T-symmetry except for the tiny, measured violation later confirmed by Cronin and Fitch. The deep equations remain almost entirely reversible. Some physicists propose the act of quantum measurement itself introduces irreversibility, since collapsing a wave function seems to only go one direction. But no complete, agreed-upon theory of measurement exists, and interpretations like many worlds argue there is no true collapse at all, only branching, which would remove the asymmetry entirely. The debate remains fundamentally unresolved, at the deepest mathematical level available to physics. Nothing requires your next breath to come after this one rather than before it. Causality as you experience it may be something added on top of the equations, not written into them. If the universe's most fundamental laws are indifferent to which way time runs, where, precisely, does the direction you're living in actually come from? Which brings every one of these entries to the same unanswered place. Number 1. The unanswered core question. Every scientist on this list, Loschmidt, Boltzmann, Penrose, Hawking, Cronin, Fitch, Eddington, was originally trying to solve something narrow and technical. None of them set out to explain why time moves forward. They stumbled into the same wall from 10 different directions. Physics, at every fundamental level checked so far, from Newton to Schrödinger to general relativity, does not require time to move in only one direction. And yet you have never once experienced it any other way. Not for a second. Not by accident. Sean Carroll summarized the state of the field bluntly in his 2010 work, stating that the arrow of time remains one of the only genuinely open foundational questions in physics. Not a solved problem being mopped up, but a live one. Entropy explains the pattern without explaining its origin. Quantum measurement explains a possible mechanism without a settled theory behind it. CP violation offers a fundamental asymmetry too small to obviously account for the scale of what you experience. None of the individual answers actually closes the case. You will read this final line moving in only one direction through time, and nothing in the deepest laws we have ever discovered required that to be true. Why does existence insist on an arrow that its own fundamental rules never asked for? The universe is not confused about time. It never has been. The equations run forward and backward with equal comfort, unbothered by our insistence on a single direction. We are the ones who cannot see it any other way, standing inside an arrow that the deepest laws of physics never actually demanded. Every anomaly on this list isn't a crack at the edge of what we know. It's sitting at the very center of our best-tested theories. Waiting. If you want to see more videos like this, click the video on screen now.